Friends, welcome to lecture number 42. In today's class, we will study about torque on a current loop. Okay, so we have taken a loop, current loop A, B, C, D, and where I have shown the direction of the current. That current loop is kept in between two magnetic poles, that is north and south pole, and you can see the brown color lines indicates the magnetic field line. So basically the current loop is kept inside a magnetic field. Okay, your BC will be equal to your AD, which is equal to W, and that is the breadth of the loop. Breadth of the loop. Okay, then your AB, which is also equal to CD, is equal to L, that is the length of the loop. Okay, fine. Now in our previous class we have studied about one thing, that is your current loop behaves as a magnetic dipole. So if you have not seen my previous lecture, please kindly see it and then come to this lecture. It will make your life simpler. Now its behavior in an applied magnetic field should be whose behavior? The current loop's behavior. Okay, should be similar to that of an electric dipole in an electric field. Okay, now the current loop should experience a torque. It should experience a torque. Okay, now let us see in which direction the forces are going to fall. You consider the AB side, and here the current is moving up. Okay, so if I apply my palm rule, which I have also told you previously, the thumb will be the direction of the current, and I will open my all four fingers in the direction of the magnetic field, and you can see the palm is pointing downwards. Therefore on AB the force will be in this direction, into the plane of the paper. Okay, force will be into the plane of the paper. Now what about the force on CD? The current is moving down, okay, and the magnetic field is, you open all your four fingers of the right hand towards the magnetic field, then you can see the palm is up. Okay, here the force will be in this direction. So what does it indicate from cross and dot? That the force experienced by these two arms AB and CD are in opposite direction, for which it will rotate in the magnetic field. Then you can ask me, sir, what about AD and BC contribution? AC and BC, there will be no contribution as theta is equal to 0 here. So no force on them. Only the force is going to fall on AB and CD, for which it will try to rotate. One force is inward, other one is outward. So it will try to rotate the current loop. Okay, so let me write this. You'll see the I have already told you what is A, what is the length, what is the width, and the loop area of the loop A, B, C, D is capital A. It is denoted by capital A, and it is placed, and the loop is placed in an uniform magnetic field B. Okay, fine. Now for sides BC and AD, your theta is equal to 0 degree. Therefore no force will fall on them. No force. Okay, but what about the force on force on AB, we have already found out it will be BIL. And what about the direction? It is into the plane of the paper. Okay, then force on CD, force on CD will be the same magnitude BIL, but it will be dot. Okay, now you see the two forces are equal in magnitude but opposite in sign. So it will try to rotate the coil, for which they will also form a torque. Okay, so we can mention here these two equal and opposite forces form a torque and tend to rotate the coil. Okay, it will rotate the coil. Now let us see how it is going to rotate it. First I will draw a magnetic field. Let me draw the magnetic field here. This is my B vector. Okay, and I am going to have a top view. I will have a top view. If I have a top view, you will see it will be of something like this. Okay, and this is your BC. This is my top view, this is my BC. Okay, which I called as a width. Okay, now what is the direction of the force? One force will be along this direction. If I take the top view, the force will be along this direction. The other one, the force will be in this direction. Remember, I am having the top view. Okay, followed. Now let me complete this right angle triangle. Let me complete it. If I complete it, because for finding out the torque I want the perpendicular distance, so let me complete this right angle triangle. Okay, this is, let it be Y, and this will be your perpendicular. Okay, and BC is having the width W. Followed. Now if I draw the normal on this will be your theta, as well as this will be your theta. Okay, now if I want to calculate the torque, now in this right angle triangle, let me find out one of the expressions. Sin theta is how much? Sin theta will be YC divided by BC. Okay, so YC will be how much? YC will be keep Y as it is. BC is nothing but the width of the current loop. So this implies my YC will be equal to W sin theta, where W is the width of the current loop. Okay, now we have told equal and opposite forces are acting, therefore you will have a torque. So tau will be equal to force into the perpendicular distance. Okay, into the perpendicular distance. So in this case, which one will be the perpendicular distance? F into YC. Okay, what is the force? BIL. And what will be your YC? Will be W sin theta. Okay, so width into length will be what? Will be the area of the coil. Okay, we know W into L is equal to A, which is area of the loop of the coil which is being used. Then what is the expression for torque? Tau will be how much? B I A sin theta. Okay, since sin theta is there, if I want to write down in vectorially, my tau vector will be how much? I A vector cross B vector. A is the area, B is the magnetic field. So this is the vectorial representation of the torque. Now if I want to incorporate the magnetic moment of the loop, okay, because we know that the current carrying loop will behave like a the magnetic dipole, which will have a magnetic moment. So now if I incorporate that, my small m vector, which is your magnetic moment of the loop, this will be equal to current I, let me write down small I A vector. This also we have studied in the previous class. Okay. So if I give it as equation 1, if I put this in equation number 1, what will be my tau? Putting this in equation 1, tau will be how much? It will be mb sine theta. So if I write down in vectorial form, tau vector will be m cross b. So this is basically a cross b be giving c vector, which will be mutually perpendicular. So all three of vectors will be mutually perpendicular to each other. So we can mention here that torque, magnetic moment and the magnetic field, all three of them are mutually perpendicular to each other. Okay. Now we have got very important notes to make from this expression, because this is needed, which will help us to solve many problems also. Okay. So the first point is, if theta is equal to 90 degree. This is a very valid, important point to understand. If theta is 90 degree, what does it mean? So theta is basically the angle between M and B. But what about the plane of the coil? Okay, so theta is equal to 90 degree. That is, in which condition? When magnetic field is along the plane of the coil. Okay, so this I can show it using a diagram also. If you have this as the plane of the coil, we'll have this, and you have got your magnetic field in this direction. Okay, B vector, your M vector will be along this. Okay, but this will be the plane of the coil. Okay, then torque will be how much? Tau will be mb sine 90. So what does it mean? It is mb, which is maximum torque. Followed? Clear? Okay, the second one. If theta is equal to 0 degree, what does it mean? Theta is 0 degree. That is, when the magnetic field is perpendicular to the plane of the coil. Okay, at that point of time, then what will be the diagram? If I draw it, it will be something like this. Okay, let me draw it again, redraw it. Fine, this is it. Okay, here it indicates that the magnetic field is perpendicular to the plane of the coil. Clear? So this is the magnetic field, and what will be the direction of M vector? It will be along this. M vector will be along this. Okay, so theta is equal to 0 degree, but the plane of the coil will be perpendicular to the magnetic field. Clear? At that point of time, what will be torque? Tau will be equal to how much? It will be mb sine 0. Sine 0 is 0, so it will be 0. That is, torque is minimum. Tau minimum. Okay. The third important thing what you will observe, if your magnetic field is uniform, that means in uniform magnetic field, your net force is equal to 0, but the net torque tau is not equal to 0. Okay, this is one of the important things which you should keep in your mind. Okay, coming to the fourth one, in non-uniform magnetic field, if the magnetic field is non-uniform magnetic field, the net force is not equal to 0, and your net torque is also not equal to 0. So the only difference is, in uniform magnetic field the net force is 0, whereas in non-uniform the net force is not 0. And here also we have got some stable equilibrium and unstable equilibrium conditions. If my M vector, which is your magnetic moment of the loop, is parallel to B vector. This is the stable equilibrium condition. Stable equilibrium condition. Okay. Whereas if M vector is anti-parallel to B vector, this is your unstable equilibrium condition. Okay, so this is about the required theory to understand the torque on a current loop. Okay, now after this we will go for a simple problem related to this. Now what does this problem tells you? It tells a circular coil. There in the derivation I have taken a rectangular coil, here the coil is circular. So a circular coil of 20 turns and radius 10 centimeter carries a current of 5 ampere. Okay, it is placed in a uniform magnetic field 0.10 Tesla. Find the torque acting on the coil when the magnetic field is applied, normal to the plane, in the plane, and total force you have to calculate acting on the coil. Okay, so here your n value, the number of turns is given as 20. What about the radius? It is given 10 centimeter. 10 centimeter means 0.1 meter. Okay, and what about the current? Current is given as 5 ampere. And what about the magnetic field? 0.10 Tesla. Then we have to calculate the area. So area of each turn of the coil, your capital A will be how much? Pi r square. That is 22 by 7. R is 0.1 whole square. It will come out to be 0.0314 meter square. Okay, now we have found out the area. Then torque on the coil, tau will be how much? It will be IAB sin theta. But remember, there n is there, so you have to multiply n, number of turns you have to multiply to it. Okay, in the first case, it is given that normal to the plane of the paper of the coil. Normal means here theta will be 0 degree. Remember this. Students make a they confuse here. Since it is given normal, they take it as theta is equal to 90 degree. It is not 90 degree. Then what will be tau? Theta equal to 0 degree. So 20 into 5 into area is how much? 0.03. Okay, into 0.1 into sine 0 degree, and sine 0 is 0, so everything goes to 0. Torque becomes 0 when the magnetic field is normal to the plane of the coil. Then the second one, here it is given in the plane of the coil. In the plane of the coil means theta is equal to 90 degree. So torque will be tau is equal to 20 into 5 into 0.03 into 0.1 into sine 90 is 1. So if you solve it, it is coming out to be 0.314 Newton meter. And the third one is telling to find the total force acting on the coil. If you remember the notes, I have told you if the magnetic field is uniform, the net force is 0. And here the coil carrying current, we know that it acts like a magnetic dipole. So force acting on the magnetic dipole in a uniform magnetic field is going to be 0. So no need to solve it. You can simply write that the force acting on the coil will be how much? It will be 0. Okay. So this is it for today's class. I hope everybody must have enjoyed it. Please do not forget to subscribe my channel. This motivates me for giving on such kind of topics which will be helpful for you. Okay. So any queries you have, you can mail me in the mail ID which is given below. Thank you for your kind patience.